Have you ever truly looked up? Not just glanced, but really looked at the night sky, letting your gaze fall into that profound, inky blackness that stretches between the pinpricks of light. It's a sight as old as humanity itself, a shared experience etched into our very DNA. But what if I told you that this seemingly simple observation, the fact that our night sky is dark, is one of the most profound clues about the universe we inhabit? What if this darkness isn't just an absence, but a silent testament, a message written across billions of years, telling us a cosmic secret? This isn't a trivial question, but a puzzle that baffled brilliant minds for centuries, a riddle known as Olbers Paradox, and its solution unlocks the very nature, age, and scale of our universe. Imagine, if you will, a vast, ancient forest, so immense, so boundless, that it stretches infinitely in every direction. If you stood within such a forest, no matter where you looked, your line of sight would inevitably fall upon a tree. There would be no gaps, no empty spaces. The entire landscape would be a solid, impenetrable wall of bark and leaves. Now, apply that same logic to the stars. If the universe were truly infinite and eternal, filled uniformly with stars, every line of sight should end on a star. The entire sky, then, should blaze with the blinding uniform intensity of the sun, day and night. It should be a cosmic inferno, a canvas of pure, unbearable light. But that's not what we see, is it? We see a tapestry of glittering points on a velvet cloak of darkness. This stark contrast between expectation and reality is the heart of the paradox. For centuries, thinkers wrestled with this discrepancy. If the universe was indeed infinite and eternal, where were all the stars? Why wasn't the night sky a dazzling, unbroken sheet of white? This simple, humbling observation whispered a truth far more complex than anyone could have imagined. The darkness wasn't just a backdrop, it was a clue. The answer, when it finally emerged, wasn't a single revelation, but a confluence of two breathtaking truths. The first truth is that our universe has a finite age. It had a beginning. Think of it this way. Even light, the fastest thing we know, travels at a finite speed. When you look at the stars, you're not seeing them as they are now, but as they were when their light first began its journey across the cosmos to reach your eyes. The farther away a star or a galaxy is, the further back in time you are looking. The universe is approximately 13.8 billion years old. This means that light from any object more than 13.8 billion light-years away simply hasn't had enough time to reach us. It's still on its way, traversing the immense cosmic distances. So, when you peer into the deepest recesses of the night sky, you are quite literally looking back to the universe's infancy. Beyond a certain cosmic horizon, there's just nothing. Not because there are no stars, but because their light hasn't had the time to complete its journey. But this finite age, while crucial, isn't the whole story. This brings us to the second, equally revolutionary truth. The universe isn't static, it's expanding. And it's been expanding ever since that fiery beginning. Imagine again our ancient forest. But now, every tree is constantly moving away from every other tree. This expansion has a profound effect on the light traveling through it. As light waves journey across the vast, expanding cosmic ocean, the very fabric of space they are traveling through stretches. This stretching causes the light waves themselves to lengthen, shifting their wavelength towards the red end of the spectrum. This phenomenon is known as cosmological redshift. The farther away a galaxy is, and the longer its light has been traveling, the more its light is redshifted. Distant galaxies have their photons stretched so dramatically that they shift out of the visible spectrum entirely, becoming infrared, microwave, or even radio waves. They are still there, emitting light, but that light arrives at our telescopes as an invisible whisper rather than a visible shout. So, the darkness isn't just about light not having arrived. It's also about light being fundamentally altered on its journey, rendered invisible to our eyes. And here lies the aha moment, the profound revelation at the heart of Olbers Paradox. The darkness of the night sky isn't emptiness. It is, in fact, a historical record. It is proof, etched in the very fabric of reality, that our universe had a beginning. And it is proof that our universe is not static, but dynamic, constantly expanding, pushing the very boundaries of what we can see and perceive. The darkness, then, isn't a void to be feared or dismissed. It's a living testament to the universe's epic journey through time and space. This initial understanding of the darkness, born from a simple observation, cracked open our understanding of the cosmos. It transformed the sky from a mere backdrop into an active participant in our story, a silent narrator of cosmic history. But this is just the beginning. The darkness of the night sky, resolved by the finite age and expansion of the universe, is only the first layer of a much deeper, more astonishing mystery. It is the visible darkness. There is an invisible darkness, a profound, enigmatic shadow that dominates our universe, making up an astonishing 95% of everything that exists. Everything we have ever seen, every star, planet, galaxy, every breathtaking nebula captured by the James Webb Space Telescope, all of it comprises less than 5% of the cosmos. The overwhelming majority of the universe remains unseen, unheard, and largely unknown. This deeper darkness isn't just the absence of light, it's the presence of something else entirely. It's a cosmic scaffolding, an unseen gravitational hand, and a mysterious repulsive force that is tearing the universe apart. This realization that the familiar luminous cosmos is merely a thin shimmering veneer over a vast, dark, and enigmatic reality is one of the most humbling and exhilarating discoveries in human history. The darkness of the night sky, a puzzle resolved, now serves as an invitation, a profound beckoning into the true hidden depths of our universe. What secrets does that overwhelming 95% hold? What invisible forces shape galaxies and dictate the ultimate fate of all things? The journey into the truly dark universe has only just begun. The journey into the truly dark universe has only just begun, and the first revelation is perhaps the most profound. The very structures that hold our galaxies together are built from something we cannot see, cannot touch, and barely understand. You see the universe as a grand cosmic ballet, a symphony of light and motion, where billions of galaxies swirl through the void. You marvel at their intricate spirals, their luminous cores, the breathtaking nebulae where new stars ignite. But what if I told you that everything you perceive, every star, planet, galaxy, every breathtaking nebula captured by the James Webb Space Telescope, all of it comprises less than 5% of the cosmos? The overwhelming majority of the universe remains unseen, unheard, and largely unknown. This deeper darkness isn't just the absence of light, it's the presence of something else entirely. It's a cosmic scaffolding, an unseen gravitational hand, and a mysterious repulsive force that is tearing the universe apart. This realization that the familiar luminous cosmos is merely a thin shimmering veneer over a vast, dark, and enigmatic reality is one of the most humbling and exhilarating discoveries in human history. The darkness of the night sky, a puzzle resolved, now serves as an invitation, a profound beckoning into the true hidden depths of our universe. What secrets does that overwhelming 95% hold? What invisible forces shape galaxies and dictate the ultimate fate of all things? The journey into the truly dark universe has only just begun. For decades, astronomers believed they understood the rules governing these celestial dances. Our understanding of gravity, codified by Newton and refined by Einstein, seemed to perfectly explain why planets orbit stars and why stars orbit galactic centers. But then, a puzzle emerged, a cosmic conundrum that challenged everything we thought we knew. Imagine a magnificent Ferris wheel spinning. You'd expect the seats closer to the center to move slower than those at the edge, right? That's how gravity works. The central hub has the most mass, exerting the strongest pull, so objects further out need to move slower to stay in orbit, or they'd simply fly off. But when astronomers looked at galaxies, they saw something utterly unexpected. This is where our cosmic detective story truly begins, and it starts with a brilliant, determined woman named Vera Rubin. In the 1970s, Vera Rubin, alongside her colleague Kent Ford, embarked on a meticulous study of spiral galaxies. She wasn't looking for revolutionary physics. She was simply mapping the speeds of stars at different distances from the center of these colossal pinwheels of light. What she found was, to put it mildly, impossible, according to the prevailing understanding of the universe. Vera Rubin observed that stars on the galactic outskirts, those far from the bright, dense centers, were orbiting at roughly the same speed as the stars much closer in. This defied all expectations. Based on the visible matter, the stars, gas, and dust we could see, those outer stars should have been moving far slower, or they would have long ago been flung into the lonely abyss of intergalactic space. It was as if you were watching that Ferris wheel, and every seat, from the very center to the very edge, was moving at the exact same rapid pace. How could this be? The only logical conclusion, Vera Rubin realized, was that there had to be far more mass in these galaxies than could be accounted for by their visible components. A massive, invisible halo of something was providing the extra gravitational glue, holding these speeding stars in place. This unseen mass, this gravitational phantom, is what we now call dark matter. Think of dark matter as the universe's invisible scaffolding, a colossal, intricate framework upon which the luminous galaxies we observe are merely the decorative lights. It's the cosmic glue that holds galaxies together, preventing them from tearing themselves apart as they spin at impossible speeds. Vera Rubin's calculations suggested that galaxies must contain about 10 times more dark mass than visible mass. While Vera Rubin's work brought dark matter into the mainstream, the first whispers of this missing mass actually came much earlier, from a somewhat overlooked figure, Swiss astronomer Fritz Zwicky. In 1933, Zwicky was studying the Coma cluster, a vast collection of galaxies. He noticed that the galaxies within the cluster were moving so fast that the cluster should have disintegrated long ago, flying apart under its own momentum. He concluded that a substantial amount of unseen dunkle materie, dark matter, must be present. Zwicky's initial estimates were astounding, suggesting the cluster contained at least 400 times more mass than could be seen. His findings, however, were largely dismissed or ignored for decades, awaiting the definitive evidence that Vera Rubin would later provide. So, what exactly is this dark matter? The truth is, we don't precisely know, but we know what it isn't. It isn't ordinary baryonic matter, the stuff that makes up you, me, the stars, and the planets. It doesn't emit, absorb, or reflect light, which is why it's so incredibly difficult to detect. If it interacted with light, we would see it. If it interacted strongly with ordinary matter, we would feel its effects more directly, perhaps even be able to capture it in our laboratories. Scientists hypothesize that dark matter is composed of exotic, hypothetical particles that are fundamentally different from the protons, neutrons, and electrons that form everything visible. Leading candidates include weakly interacting massive particles, or WIMPs, and axions. These particles, if they exist, would pass right through us, through the Earth, and through entire galaxies without leaving a trace, like ghosts in the machine, only revealing their presence through their collective gravitational pull. The search for these elusive particles is one of the most active and exciting frontiers in physics today, with experiments deep underground and in space trying to catch even the faintest whisper of a dark matter interaction. This invisible scaffolding isn't just a localized phenomenon within galaxies. It shapes the entire large-scale structure of the universe. Imagine the cosmos not as a random sprinkle of stars, but as a vast, intricate cosmic web, a three-dimensional network of filaments and knots, almost like a colossal brain. This web is primarily made of dark matter, with galaxies forming at the densest intersections and along the filaments, like luminous pearls strung along invisible threads. One of the most compelling pieces of evidence for dark matter, beyond galaxy rotation curves, comes from a phenomenon called gravitational lensing. Just as a glass lens can bend light, a massive object in space, like a huge galaxy cluster, can warp the fabric of space-time around it, bending the light from even more distant objects behind it. When astronomers observe these clusters, they see strange, distorted arcs and multiple images of faraway galaxies. The amount of bending tells us the total mass present in the cluster. And time and again, the amount of mass required to produce the observed lensing effects is far greater than the visible matter alone can account for. Gravitational lensing allows us to literally see the invisible hand of dark matter in action, making its presence undeniable. This realization, that approximately 27% of our universe is composed of this enigmatic dark matter, a substance that binds galaxies and clusters together, is a staggering shift in perspective. Our familiar universe, bright and bustling, is merely a surface phenomenon, a map, an ocean of unseen gravitational influence. And yet, dark matter is only one part of the 95% mystery. Remember that other overwhelming component of the dark universe? The one that accounts for roughly 68% of everything? That's dark energy. It's crucial to understand that dark matter and dark energy are fundamentally different. While dark matter is a gravitationally attractive force, clumping together to form cosmic structures, dark energy is a mysterious, repulsive force, a property of space itself that is pushing everything apart. It's like the universe has an invisible, accelerating engine running in the background, constantly increasing the distances between galaxies, not binding them. The universe is not just dark. It's expanding at an ever-increasing rate because of this pervasive, uniform, repulsive force. This cosmic loneliness, this humbling insignificance, is a powerful and almost spiritual realization. Our entire existence, the entirety of human history, every star we've ever gazed upon, every galaxy photographed, is a luminous whisper in a universe dominated by silence and shadow. We are living on the decorative lights, unaware of the immense unseen girders holding our entire cosmic reality in place. The implications are profound, inviting us to look beyond the immediate, beyond the visible, and to truly contemplate the vast, hidden depths of existence. The darkness of the night sky, once a simple backdrop, is now a portrait of an unknown reality, a testament to the universe's boundless secrets. And we are only just beginning to read its hidden messages. For generations, humanity looked up at the night sky and saw a canvas of infinite, sparkling points. We mapped the constellations, charted the planets, and eventually gazed out at billions of galaxies, each a shimmering island of stars. It was a universe of light, a testament to the visible, tangible cosmos. But what if I told you that everything you've ever seen is merely a whisper in a symphony of silence? What if I told you that the universe we perceive is less than 5% of what truly exists? This isn't just a philosophical musing. It's a scientific revelation that has fundamentally reshaped our understanding of reality. A cosmic detective story that began with a curious case of missing mass. Imagine for a moment the year 1933. A brilliant, albeit eccentric, Swiss astronomer named Fritz Zwicky was peering through his telescope at the Coma cluster, a vast collection of galaxies. He was meticulous, observing the galaxies, measuring their speeds. What he found was baffling. The galaxies were moving so incredibly fast, far too fast to be held together by the gravitational pull of the visible matter alone. By all accounts, they should have been flung out into the cosmic void, scattering like marbles across a table. Yet, they weren't. Zwicky, with a flash of insight, concluded there must be some immense, unseen gravitational glue holding them in place, a vast amount of dunkle materie, or dark matter as he called it. His calculations suggested the cluster contained at least 400 times more mass than could be accounted for by its visible stars. It was a radical idea, a challenge to the very foundation of physics, and for decades it was largely dismissed, a peculiar footnote in the annals of astronomy. The scientific world wasn't ready to accept that the universe was hiding such a profound secret. But the universe, as it turns out, is full of secrets, and it rarely keeps them forever. The stage was set for another trailblazing astronomer, Vera Rubin, to pick up the thread of this cosmic mystery in the 1970s. Imagine her, a woman in a field often resistant to female voices, steadfastly pursuing her research. With her colleague Kent Ford, she began studying the rotation curves of spiral galaxies. Think of a merry-go-round. The horses on the outer edge move faster than those closer to the center to complete a rotation in the same amount of time. You'd expect something similar in a galaxy, with stars further out, orbiting slower because they're feeling less gravitational pull from the central mass. But that's not what Vera Rubin found. Instead, she observed that stars on the galactic outskirts were orbiting at roughly the same speed as stars near the center, defying all known Newtonian physics. It was as if an invisible, massive halo was surrounding each galaxy, extending far beyond the visible stars, providing the extra gravitational tug needed to keep everything from flying apart. Her calculations showed that galaxies must contain about 10 times more dark mass than visible mass. This was incontrovertible evidence, a definitive answer to Zwicky's decades-old puzzle. Dark matter was real, an invisible scaffolding, a cosmic skeleton upon which galaxies were built and held together, making up approximately 27% of the universe's total mass energy content. The universe, you see, is far stranger and more magnificent than we ever dared to imagine. As we peer deeper into its dark canvas, the hidden messages we've begun to decipher tell a story not of finality, but of an unfolding cosmic drama. We left off contemplating a future shaped by an accelerating expansion, a universe destined for solitude and cold. But what if that future, like our understanding, is also still evolving? What if the very forces driving that expansion are themselves changing? For decades, humanity has been diligently charting the cosmos, meticulously adding details to what we call the standard model of cosmology. Think of this model as our most exquisite, intricate map of reality. It's a breathtaking achievement. This map has guided our exploration, allowing us to navigate the known universe with incredible precision. It tells us that everything we've ever touched, seen, or felt, every star, every planet, every shimmering galaxy, makes up less than 5% of all that exists. The rest, that's where the true enigma lies. Roughly 27% of this cosmic map is shaded with a mysterious label: dark matter. We can't see it. It doesn't interact with light, but its gravitational pull is undeniable. It's the invisible scaffolding upon which galaxies are built. Its existence was first hinted at in 1933 by a pioneering but largely ignored Swiss astronomer named Fritz Zwicky, who noticed galaxies in the Coma cluster moving far too fast. He called it dunkle Materie, dark matter. For decades, his observations were a scientific whisper in the wind. But then, in the 1970s, a brilliant American astronomer named Vera Rubin, often battling institutional skepticism, provided the incontrovertible evidence. She charted the rotation curves of spiral galaxies, expecting to see stars at the edges slow down. Instead, she found them orbiting at the same speed as stars, closer to the galactic center, as if an immense, invisible halo of mass was exerting its gravitational grip. Her calculations showed that galaxies must contain about 10 times more dark mass than visible mass. Her work transformed Zwicky's whisper into a roar, cementing dark matter's place in our cosmic map. We've learned to see this invisible giant through its effects, through the way it gravitationally lenses and distorts the light from distant galaxies, bending space-time itself. And then the other, even more profound unknown: dark energy, accounting for a staggering 68% of the universe. This isn't matter at all, but a repulsive force, a property inherent to the very fabric of space, pushing everything apart. Its discovery in 1998 was a seismic event. Two teams were studying distant Type Ia supernovae, cosmic lighthouses known as standard candles because of their consistent brightness. They expected to find the universe's expansion slowing down. Instead, to their utter shock, they found it was speeding up. The universe was not decelerating, it was accelerating. This discovery, which earned the Nobel Prize in Physics in 2011, meant our carefully constructed map of the cosmos was missing its most dominant feature. Our map, once thought to be near completion, now revealed a massive, uncharted continent, a sprawling, mysterious territory that utterly dominates the cosmic landscape. We discovered the darkness. We mapped its distribution. We measured its effects, and we believed we understood. But here's where the cosmic detective story takes its most thrilling, most disorienting turn. Because the latest clues aren't merely adding detail to our map. They're telling us that our map, as beautiful and intricate as it is, might be fundamentally flawed. The first, most pressing clue comes from what scientists now call the Hubble tension. You see, there are two primary ways we measure the expansion rate of the universe, a rate we call the Hubble constant. One way involves looking back to the very early universe. Missions like COBE, WMAP, and Planck have meticulously mapped this ancient light, providing us with incredible precision. These early universe measurements suggest an expansion rate of about 68 kilometers per second, per megaparsec. It's a consistent, elegant measurement. However, there's another way. By looking at the local universe, observing objects like those very same type Ia supernovae. These measurements, using powerful telescopes like Hubble and Webb, allow us to directly observe how fast galaxies are moving away right now. And here's the rub. These direct local measurements consistently suggest a faster expansion rate, closer to 73 kilometers per second per megaparsec. Do you feel that? That's the tension. A difference of just 5 might sound small, but in cosmology, it's a chasm. It's a fundamental disagreement. It's like having two perfectly calibrated clocks and finding they consistently show different times. Which one is right? Or does our understanding of space-time itself need to be reevaluated? This is a potential crack in our cosmic map. This discrepancy could mean several things, each more mind-bending than the last. It could mean the universe is younger than we thought. It could mean there's an entirely new, unknown component of reality at play. Or it could mean that dark energy itself is not the simple, constant force we assumed it to be. And that brings us to the second clue. Hints that dark energy might not be constant. Our current model assumes it's a fixed, unchanging property of space. But recent observations suggest it might be dynamic, evolving, perhaps even weakening. Imagine the force pushing the universe apart isn't a steady hand, but one that subtly changes its grip. What would that even mean? If dark energy has varied, it could resolve the Hubble tension. It could mean our understanding of the past doesn't perfectly predict the present, because the rules of the game have subtly changed. The big freeze or big rip scenarios we once contemplated are themselves contingent on a force that might be far more mercurial. This isn't an ending. It's an exhilarating beginning. We are not at the conclusion of our journey. We are standing on the brink of another scientific revolution, a moment where everything we thought we knew might once again be gloriously, beautifully, and terrifyingly rewritten. The darkness of the universe, once a symbol of what we couldn't see, is now an active, vibrant frontier, inviting us to redefine our place within its ever-unfolding enigma. For so long, we stood on the shores of the known, gazing at a cosmos we thought we understood. We charted the stars, mapped the galaxies, and felt the comforting warmth of the light they cast. We, humanity, were like children playing on a beach, marveling at the intricate patterns in the sand beneath our feet, convinced this small, sun-drenched patch was the entirety of the world. What we didn't realize, what we couldn't grasp, was that beyond the familiar dunes lay an ocean so vast, so deep, and so profoundly dark that it swallowed 95% of reality whole. This isn't a reason for despair. It is the ultimate invitation. It's a beckoning from the unexplored deep, a whisper across the cosmic waves that calls to our deepest, most inherent human curiosity. Imagine the sheer wonder of discovering that everything you have ever seen, every star that twinkles in the night sky, every planet, every nebula, every galaxy stretched across the canvas of existence, constitutes less than 5% of the total mass energy content of the entire cosmos. Think about that for a moment. All the radiant beauty, all the luminous grandeur, all the visible matter that has fueled our dreams and scientific pursuits for millennia is just a tiny, sparkling fraction. The overwhelming majority, a staggering 95%, remains utterly invisible, enigmatic, and profoundly unknown to us. This fact, this breathtaking 95% reveal, is the central wow moment of our cosmic journey, the ultimate mystery beckoning us forward. It makes you wonder, doesn't it? If the universe is so full of stars, why is the night sky dark? This simple question, known as Olbers Paradox, perplexed thinkers for centuries. If the cosmos were infinite and eternal, teeming with stars in every direction. Then every line of sight should eventually land on a star, making the night sky as bright as the surface of the sun. But it isn't. The solution to this paradox, a cornerstone of modern cosmology, tells us something fundamental about our dark universe. It has a finite age, approximately 13.8 billion years old, and it is expanding. This means light from the most distant stars hasn't had time to reach us, and the light that does travel across the vastness of space is stretched and redshifted out of the visible spectrum by the universe's expansion. The darkness, then, is not an absence, but a profound indicator of time and cosmic scale, a silent testament to the universe's beginning. But the darkness we speak of now goes far beyond the limits of visible light or cosmic horizons. It is a darkness woven into the very fabric of reality itself, a pair of fundamental components that dominate the universe: dark matter and dark energy. Together, these two unseen titans account for roughly 95% of everything that is. First, let's turn our gaze to dark matter, a mysterious substance that does not emit, absorb, or interact with light or any other form of electromagnetic radiation. It is utterly transparent, a ghost in the cosmic machine, yet its gravitational presence is undeniable. Approximately 27% of the universe is composed of this enigmatic material. The first inkling of this missing mass came in 1933 from the keen observations of the Swiss astronomer Fritz Zwicky. He was studying the Coma cluster, a vast collection of galaxies, and noticed something astonishing. The individual galaxies within the cluster were moving at such incredibly high velocities that, based on the visible matter alone, they should have long since flown apart. Zwicky, a man ahead of his time, concluded that a vast amount of unseen dunkle materie, or dark matter, must be providing the extra gravitational glue to hold the cluster together. His calculations suggested the cluster contained at least 400 times more mass than could be accounted for by its visible stars, a truly revolutionary idea that was largely dismissed by the scientific community for decades. It wasn't until the 1970s that the idea of dark matter truly entered the scientific mainstream, thanks to the pioneering work of American astronomer Vera Rubin. Her story is one of unwavering dedication and scientific brilliance, often in the face of institutional sexism. Along with her colleague Kent Ford, Rubin began studying the rotation curves of spiral galaxies. Newtonian physics predicted that stars on the outer edges of a galaxy should orbit much slower than those closer to the center, just as the outer planets in our solar system orbit more slowly than the inner ones. But what Rubin observed defied all expectations. Stars on the galactic outskirts orbited at roughly the same speed as stars near the center. This cosmic ballet could only be explained if there was a massive, invisible halo of matter surrounding each galaxy, providing the extra gravitational pull needed to keep the outer stars from flying off into space. Her meticulous calculations showed that galaxies must contain about 10 times more dark mass than visible mass. Vera Rubin's incontrovertible evidence for dark matter cemented its place in modern cosmology, fundamentally changing our understanding of how galaxies form and are held together. Dark matter acts as an invisible gravitational scaffolding, a cosmic web upon which galaxies are built and intertwined. Beyond the pull of dark matter, there's an even more pervasive and perplexing force at play: dark energy. This isn't gravitationally attractive like dark matter. Instead, it is a repulsive force, a property of space itself, that accounts for roughly 68% of the universe. Dark energy is responsible for the accelerating expansion of the cosmos, a discovery that fundamentally shook the foundations of cosmology in 1998. Scientists had long assumed that the universe's expansion, set in motion by the Big Bang, would be gradually slowing down due to the collective gravitational pull of all the matter within it. But two independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, co-led by Brian Schmidt and Adam Rees, were in for a monumental surprise. They were using distant type Ia supernovae as standard candles, astronomical objects with a known intrinsic brightness, to measure cosmic distances. By comparing their known luminosity to their observed faintness, astronomers can calculate how far away these stellar explosions are. What they found was utterly baffling. These distant supernovae were fainter than expected, implying they were further away than they should have been if the universe's expansion was decelerating. The only conclusion was that the universe's expansion was, in fact, speeding up. This shockwave of a discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. This accelerating expansion led to the reintroduction of a concept Albert Einstein had once called his biggest blunder, the cosmological constant. Einstein had initially introduced this term into his equations of general relativity to achieve a static universe, a notion he abandoned after Edwin Hubble discovered the universe was expanding. Now, this blunder was resurrected, understood as the manifestation of dark energy, an intrinsic property of space that causes it to expand at an ever-increasing rate. Dark energy is fundamentally different from dark matter. While dark matter clumps together and exerts a gravitational pull, dark energy is a smooth, uniformly distributed repulsive force pushing everything apart. Its density is incredibly low, estimated at around 7 × 10⁻³ grams per cubic centimeter. But because it is uniformly present everywhere, it dominates the universe on the largest scale. Our modern understanding, refined by missions like COBE, WMAP, and Planck, which have mapped the cosmic microwave background, the faint afterglow of the Big Bang, with increasing precision, confirms this dark composition. The universe is approximately 68% dark energy, 27% dark matter, and a mere 5% ordinary baryonic matter. Dark matter, though invisible, forms the structural backbone of the universe. Imagine a vast, intricate network of invisible filaments stretching across billions of light years like an immense cosmic spiderweb. This is the cosmic web, a breathtaking large-scale structure where galaxies cluster along the dense strands and voids of empty space lie between them. It's this scaffolding of dark matter that dictated where and how galaxies would form, shaping the universe into the grand, interconnected tapestry we observe today. So, here we stand, you and I, on the edge of this vast, dark ocean. The sand beneath our feet, the mere 5% we can see and touch, is familiar. But the unexplored deep, the 95% that beckons, is where the true adventure lies. This isn't about fear of the unknown. It's about the exhilaration of discovery. Our cosmic insignificance, the humbling realization that we are but a tiny flicker in an overwhelmingly vast and dark cosmos, is not a curse. It is the very thing that makes our brief, conscious moment of understanding, our ability to even ask the question, how dark is the universe, so infinitely precious. This journey into the darkness is ongoing. Scientists are tirelessly seeking to make the invisible visible. Gravitational lensing, where dark matter's immense gravity bends and distorts the light from distant galaxies, allows us to literally see the effects of its unseen presence, like peering through a warped window to glimpse the hidden architecture of the cosmos. Deep underground laboratories are attempting to detect hypothetical particles, like weakly interacting massive particles, WIMPs, or axions, the leading candidates for what dark matter might be composed of, hoping to catch a fleeting interaction with our visible world. And the story continues to unfold, with new scientific cliffhangers emerging, like the perplexing Hubble tension. Measurements of the universe's expansion rate from the early cosmos suggest a different rate than measurements from the local universe. This discrepancy could imply new physics beyond our current understanding, or perhaps an even younger universe than we currently calculate. The ultimate fate of the universe, too, hinges on the nature of this darkness. Will the accelerating expansion, driven by dark energy, lead to a big freeze, where the universe expands into infinite cold and emptiness? Or perhaps a big rip, where the repulsive force grows so strong it tears apart galaxies, stars, and even atoms? Could the current trends reverse, leading to a big crunch? These are not just theoretical musings. They are potential harbingers of a radical new understanding of reality. This isn't an ending. It's an exhilarating beginning. This is why the cosmic detective story is far from over. In fact, the latest clues are making the mystery deeper, more thrilling, and more profoundly humbling than ever. We thought we had a coherent picture of the universe, a nearly complete map. But these new discoveries are revealing that our map has not just uncharted territories, but perhaps entirely new physical laws waiting to be written. We are not at the conclusion of our journey to understand the universe. We are standing on the brink of another scientific revolution, a moment where everything we thought we knew about the cosmos might once again be gloriously, beautifully, and terrifyingly rewritten. The darkness of the universe, once a symbol of what we couldn't see, is now an active, vibrant frontier, inviting us to redefine our place within its ever-unfolding enigma.